Hello everyone, welcome to the video lecture on differential equations and its applications. Today we will discuss the properties of Legendre polynomials. In the previous class we have seen the introduction to Legendre polynomials and some of its properties including the Rodriguez formula. So before this section, let us have a review of our previous class on Legendre polynomials. Now we started with the Legendre's equation, which is a differential equation 1 minus x square into y double dash minus 2xy dash plus n into n plus 1 into y equal to 0, where n is a non-negative integer. And in one of the previous section, we using Frobenius series, we found the solution to this equation, and we have seen that the radius of convergence of that power series is 1. That is, all the solutions of this equation are analytic on the interval minus 1 less than x less than 1. Now we could see that the solutions most useful in the applications are those bounded near x equal to 1. So what we do is that we bring a change in the independent variable from x to t by setting t is equal to half into 1 minus x, so that x is equal to 1 corresponds to t is equal to 0. Okay, so when we apply this change, we could see that this t is equal to 1 minus x, so 2t is equal to t is equal to half 1 minus x, so 2t is equal to 1 minus x, and therefore x is equal to say 1 minus 2t, and what is 1 plus x? 1 plus x 2 minus 2t, that is 2 into 1 minus t. Now using this you can replace this part with 1 plus x into 1 minus x. Okay, and how to replace this y double dash? We can see that dy by dx is dy by dt into dt by dx. So dt by dx from here you can see that is minus 1 by 2. So this is what your dy by dx is, and d square y by dx square is equal to d by dx of dy by dx, that is d by dt into dy by dx, dy by dt of dy by dx into dt by dx, which is minus 1 by 2. So again you can replace the dy by dx with the dy by dt into minus 1 by 2, so which takes you to 1 by 4 into d square y by dt square. So in this way you can find the replacement for all the variables and y double dash and y dash, and hence finally obtain this equation, this new equation in terms of the variable t, that is t is into 1 minus t into y double dash plus 1 minus 2t into y dash plus n into n plus 1 into y equal to 0. Now we can see that this is in the standard form of a Gauss hypergeometry equation, so that if possible we can find a general solution using the previous techniques. That is, let us compare it with the Gauss hypergeometry equation. But we can see that here the values of a, b and c are like this, and here c is an integer. But we know that when c is not an integer, then we can find the general solution of Gauss hypergeometry equation in this form near the singular point x is equal to 0. But since c is equal to 1, we can only ensure the first part of the of this solution. Thus, at t equal to 0, we could obtain the solution y1 is equal to f of minus n comma n plus 1 comma 1 comma t, and using a technique by putting y2 is equal to vy1, we could obtain y2 is equal to y1 into log t plus a1t plus etc. Now we have the general solution y equals c1 y1 plus c2 y2. However, since log t is a part of y2, we can see that to ensure the solution is bounded near x equal to 1, we can obtain such a solution only when this c2 is equal to 0. Okay, so all the solutions that are bounded near x equal to 0, x equal to 1 are of the form y equal to z1 y1, that is the multiples of y1, which is denoted by capital F of minus n comma n plus 1 comma 1 comma t, which we call as the nth Legendre polynomial, and we denote it with the Pn of x. So we have Pn of x is equal to f of this part, where you already know the expansion of f of abcx, which is 1 plus minus n into n plus 1 by 1 factorial into 1 minus x by 2 plus etc. Now we could see in the previous chapter that this Pn of x actually takes the form as in this expression, and once again applying the binomial formula, we can see that this Pn of x is actually 1 by 2 raised to n into n factorial into nth derivative of x square minus 1 all raised to n with respect to x. This expression of Pn of x is called Rodriguez formula. Then in the previous class itself, we also found some first few Legendre polynomials using this Rodriguez formula, that is P0 of x equal to 1, P1 of x equal to x, and P2 of x and P3 of x. So here you can see the graphs of first few Legendre polynomials. You can also note that the degree of the nth Legendre polynomials is n.